Hello, I'm Giordano Scapucci, and I'm a group leader at QTech, TU Delft. My group develops Group 4 materials for quantum technologies, and today I will tell you more about electrical characterization of germanium quantum wells, which are at the foundation of this IGNITE project. So by the end of this lecture, you should be able to discuss the electrical properties of germanium silicon germanium heterostructures for spin qubits, explain the influence of the thickness of the silicon germanium barrier on the electrical properties, and explain the influence of the silicon germanium buffer on the electrical properties of the quantum well. So I have also put here on the screen a recent review that we wrote with other co-authors from the community about using germanium for quantum information. And just as a reminder, these planar heterostructures that we will now see how we will characterize them electrically. The key property is that by confinement, you will split the two bands, the two valence bands. So essentially, we are dealing with a single band whole, two-dimensional whole gas. So why is electrical characterization of the base material for qubits so important? It is important because it's a key step in the whole development cycle of spin qubits. So you see here 3 blocks that are important. The first one is actually designing, growing, and characterizing from a structural way the heterostructures. So we do this using reduced pressure chemical vapor deposition, which is the same technique that industry uses for microelectronic industry to make transistors. We start with a silicon wafer, and then we grow the whole heterostructure on top. And you see in these images a electron microscope image of a strange germanium quantum well that we grow in our labs routinely here at TU Delft. So once we actually make the material and look at its structural properties, the second step is to electrically characterize it. To do so, we fabricate devices on a 4-inch wafer, and we fabricate many of them because we are interested in electrical properties in a statistical way. So we want to understand how uniform is the wafer by measuring these properties across many different devices. We do this also at cryogenic temperature, and our main toolbox is two-dimensional quantum transport. So this electrical characterization is part of the first feedback loop that we perform. Finally, what we want to do is also gather information not from macroscopic devices such as Hall bars or transistors, but we want to gather information more at the local scale, at the nanoscale. So the idea here for the second feedback loop is to measure quantum devices as statistical local probes of qubit environment. So by measuring the strained germanium channel, what we learn is the electrostatic landscape and the disorder around the qubits. Now let me tell you a little bit more about the most important device that we make and characterize for gaining information about the strange germanium quantum well. This is the Hall bar heterostructure field effect transistor. So it's essentially like a transistor where you have a channel here that is contacted by source and drain electrodes, and the carriers are induced in this channel by applying a voltage at the top gate. So this is essentially as a transistor, but embedded in a heterostructure, hence the name heterostructure field effect transistor. Now the shape of this transistor is quite different from the ones that we actually use in our conventional computers, because it has this shape of a Hall bar. So if you look at it from the top, we have 6 ohmic contacts, so as 2 to pass a current or to apply a voltage, and the other 4 is actually to measure the voltage, the longitudinal voltage, or the transverse voltage in a 4-terminal configuration. So essentially, we can measure the current, the longitudinal voltage, and the transverse voltage. Now, the top gate is very important because by changing the top gate, we not only accumulate the channel, but we can also change the density in that two-dimensional whole gas that we accumulate. So these are all the metrics that we measure. So Vxx, Ixx, so on and so forth. And using these formulas, we can essentially gain information about the resistivity of the two-dimensional whole gas. And by using the Hall effect, so applying a perpendicular magnetic field to the device, we can also measure the slope of the transverse resistance, and via the Hall effect, we measure the density. Now, what metrics are we looking in these two-dimensional whole gases, and why do we care about? So the first metric, which is one of the most important ones, is the carrier mobility measured by the Hall effect, and hence it's called the Hall mobility. This is to distinguish it by the field effect mobility that we measure in transistors. And associated with the Hall mobility is the mean free path. So measuring this Hall mobility at low temperature will help us to assess the disorder potential in the channel. So in a nutshell, the mobility is and the mean free path are defined in the following way. So the mobility quantifies the response of a charge carrier to an electric field. So how fast does it travel through the semiconductor when pulled by an electric field? And it's defined via the drift velocity here. And this is the relationship that links together the drift velocity and tau, which is the scattering time between the collisions. So you have to think of a charge here, electron or a hole that is traveling through your semiconductor, and it will feel scattering centers. And the mean free path is the time it travels between the scattering events. Now, the interesting part is that the mobility is well related to conductivity, resistivity, and density, which are all measurable via the Hall effect, as I said before. And so you can essentially measure mobility in these two-dimensional whole gases. Now, in this picture here, which is taken from the review article I was mentioning just earlier, you see how the material through the decades have been improved, and you see a correlation with the mobility. So we were studying back in the 90s with the first quantum wells with mobilities below 10,000. Then a big improvement in the way we made the silicon germanium buffer layer underneath the quantum well brought us to mobilities around 100,000. And then in around 2008, 2009 onwards, another improvement in the silicon germanium buffer layer underneath the quantum well took two-dimensional whole gas to reach mobilities of about 1 million or even larger nowadays. And this is very important because this means that now the quality of this material is so high and the disorder is so low that we can think of bringing together many quantum dots and many qubits and hope that the yield of these devices will be very high because the disorder is very low. Now, another metric that we like to measure that is very informative is what is called the percolation density. So the percolation density is the minimum density that you need in the channel to achieve metallic conduction. It characterizes disorder at the low density, which is actually the same regime where quantum dots operate. So you can think of percolation density in the following way. It's like it's essentially the minimum density that you need to overcome all the disorder landscape in the channel. And for example, here in this graph, you may see if there's no electrons, you see these mountains here represent the disorder, and so you have a connection of metallic states and insulating states. If you start rising the Fermi sea level, at some point you will overcome all this disorder and have a metallic conductive channel. So the lower the percolation density, the lower the disorder and the inhomogeneities in the material will be. And so essentially in a quantum well FET, we're looking for high mobility and low percolation density. So when we measure these mobility density curves, which are the mobility at a specific density and then repeat as a function of density, we really look at this part of the curve, which tells us what is the maximum mobility once you saturate the quantum well with density, with charges, and what is the minimum density to enable conduction in the channel. And you get these informations by simply measuring mobility density curves. Also, you can do a more elaborate analysis of these curves by looking at the shape, and usually this follows a power law, and by the exponent of this power law, you will learn a bit more about the scattering mechanism that are limiting transport in these two-dimensional systems.